What is the problem we want to address today? It is a familiar problem of a particle or an observer moving along the x-axis at some constant acceleration g. Yeah? So what is the solution? You know, this is the solution that Galileo found even before Newton. The distance covered is proportional to the square of the time elapsed. And if you start at rest, the velocity after some time t is u equals gt or at. This is okay, no? This is the non-relativistic solution. You can immediately see a problem with it. Can you say what's the problem with it from special relativity point of view? Yeah, if you wait for a very long time, the speed will cross the speed of light. So in relativity, this solution is not acceptable, neither is this. And this is the problem we want to solve. If I want to, so it is a one-dimensional problem only. How does the distance change as a function of time? How does the speed change with a function of time? If I have to obey special relativity, yeah, that is the problem. And if you plot s as a function of t, it is a parabola. If you then, or you can write t going as s to the half. So you want to plot t going as s to the half. So what is it? T going as s to the half. So I want to plot t as a function of s at s equal to 0, 0. So something like this. This is the opposite of a parabola. S goes to infinity, t goes to infinity, and what is the slope? dt by ds is 1 over root s. So as s goes to infinity, the slope goes to 0. It's okay, no? So, so curve that will go to 0 slope at infinity, and we are going to compare. This is a space-time diagram, and this is the trajectory. We want to see what is the trajectory in this space-time diagram if I have to do this according to special relativity. Yeah? Okay, right. So the answer to that problem is has something to do with what are called Rindler trajectories. The trajectory of a accelerated or uniformly accelerating observer in special relativity is called Rindler trajectory. And we will also ask what are the natural coordinates to use for a uniformly accelerating observer. Those are called Rindler coordinates. And very interestingly, there is a concept of a space-time horizon. All of this is now happening in flat space-time, no gravity, except that you can interpret this uniform acceleration as a uniform gravitational field in the opposite direction because of the equivalence principle. But there is no curvature. If you have a uniform gravitational field, the Riemann curvature tensor is 0 because we are in flat space-time. Okay? There is no gravity, and yet there are some properties very similar to those of a black hole. So it's interesting to try to understand that. Okay. There is another motivation for studying this problem, and that is the so-called twin paradox, which you remember from special relativity. There's a pair of twins, one here at the Earth, and another one who travels, let's say, at a speed close to the speed of light, goes up to some star and comes back. Moving clocks slow down. Yeah? So let's say this is twin A, this is twin B. Twin A will conclude because this fellow was moving, he will, when he comes back, he'll be younger, be older. The one who stayed back is older. but the guy who moved, because moving clocks slow down, this guy will come back younger. But this fellow can say, no, I didn't go anywhere. You were moving. Yeah, relativity. Yeah. So this fellow wants to say, no, you are younger. So both can't be younger. And they come back. This is a real life situation. Only one of them is younger. And what is the answer to that paradox? See, both are not inertial observers. This guy is staying put. This fellow, when he starts from rest, is accelerating. Yeah? And then he stops. He again accelerates. His speed is changing. There is a huge acceleration here. So this fellow is suffering acceleration. This fellow is not. So they are different. Both are not inertial observers. One has accelerated. So we want to find out now, knowing that one of them has accelerated, who is younger or older. That problem can also be solved. It's a fun thing to do. So let us get going. We want to define 4 acceleration and something known as the momentarily co-moving rest frame, MCRF. Yeah, we'll do that. Define 4 acceleration AI is dui by d tau, the rate of change of 4 velocity per unit proper time. Tau is the proper time. You understand the proper time, right? ds square equal to dt square minus dx square. That ds square is proper time, or you call it d tau square. It is the rate at which a clock runs in the rest frame of the observer. Okay? So if the observer is accelerating, he has a clock, he or she, so please pardon my he's and she's, it's they. The observer has a clock with them, and the time measured by that clock is this proper time tau. Now, you recall this from special relativity, that the magnitude of the 4 velocity is a constant. It's minus c square, minus because I am using minus plus 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 coordinates signature, otherwise it's plus. Are you okay with this? You've been told this in special relativity. Yeah? So Bhaswati covered special relativity? No? She's doing something else, is it? Okay. Anyway, if you have a doubt with this, just ask me. I can prove it for you. This is very simple. The invariant scalar product of the 4 acceleration with the 4 velocity is 0. This is also, oh, I made a mistake. This is not AI. This is UI. Please correct it. Huh? I'll correct it in the notes. UI is a constant, minus c square. D by d tau of UI is hence 0. Because this is a constant, its time derivative is 0. This is a typo here. This is not AI. This is UI. After derivation, you will get a factor 2 because the d tau acts on both the UIs. So since this is 0, this dot product, this scalar product is 0. The 4 acceleration we can think of as being orthogonal to the 4 velocity. Note that this does not happen with the 3 acceleration. On ordinary classical mechanics, the acceleration is not having a 0 dot product. In fact, you know, you are moving along x-axis, your acceleration is also along the x-axis, the dot product is non-zero. Yeah? Okay. To understand the meaning of 4 acceleration, let us introduce the momentarily co-moving rest frame, a Lorentz frame that at least for one moment has the same velocity as the accelerating observer. An accelerating observer is at rest in the MCRF for one moment. What does it mean? I start from here, I am accelerating, my speed is changing. I come here, I have a speed v. Imagine that there is a Lorentz frame, inertial frame moving with the same speed v that I am having here. So for a moment, I am at rest with respect to that fellow. He is always moving at some fixed speed, but my speed is increasing. but for one instant I will be at rest with him. So, at different points, different MCRFs. You understand? Stop me anytime something is not clear. In the MCRF, I am momentarily at rest. Okay? So, in the MCRF, the accelerating observer has the following property. So, I hope you have understood what is the definition of an MCRF. Okay. In the MCRF, since I am momentarily at rest, my d tau will be dt MCRF. I am at rest with respect to that fellow. At that moment, there is no change in the coordinate position. We are at rest with respect to each other. So, d tau is dt MCRF. I am at rest, so the spatial components of my 4 velocity with respect to the MCRF are 0. There is only a time component of the velocity, and since d tau and dt are equal, the time component is c, because the time component of the 4 velocity is c dt by d tau. You understand? And dt and d tau are equal, so the time component is c. So, what are we saying? The velocity components of the accelerating observer as measured with respect to the MCRF, momentarily co-moving rest frame, is this. Time component is c, spatial components are 0. I use this to calculate the acceleration, which is dui by d tau. Okay? So, the 0th component of the 4 velocity is a constant. So, the 0th component of the 4 acceleration is 0, and dt is equal to d tau. So, spatial components of the 4 acceleration are these. Yeah, the velocity is 0, but the acceleration is not 0. My velocity is going to change with respect to the MCRF. After some moment, there will be a new MCRF. You get this? I hope it's okay. Yeah. So, I am accelerating at this instant. I am at rest with respect to this guy MCRF. So, 4 velocity is given here, and F4 acceleration, the time component is 0, but the spatial components are non-zero and given by this. What is the magnitude of this fellow? If the magnitude is a square, if the magnitude of the 4 acceleration is a square, then a square is equal to the square of the 3 acceleration. Yeah, that is obvious, no? Take the square of this, only this contributes. A is the magnitude of the acceleration experienced in the MCRF. So, that is the interpretation of the magnitude of the 4 acceleration. If I have a 4 acceleration a square, that is a different quantity from 3 acceleration. The 4 acceleration a is equal to the 3 equal to the magnitude of the acceleration as experienced in the MCRF. In the MCRF, I am an accelerating particle. I am an accelerating observer in the MCRF, and how much is my acceleration as measured in the MCRF? It is the same as the magnitude of the 4 acceleration. That is, a is the acceleration that the observer feels in their own rest frame. If you are at rest with respect to the MCRF, that is the same as your own rest frame. In your rest frame, you feel the acceleration a. Okay. Now, let us solve for the trajectory of the uniformly accelerating observer, namely non-relativistic s equals half gt square or x equals half gt square. I want the relativistic solution for instead of x equals half gt square. For small accelerations and at small times, that should reduce to x equals half gt square, yeah? Whatever relativistic expression we want to find out. Imagine an observer who starts at rest with respect to us and moves with an acceleration 10 meters per second square along the x direction. The g can be anything. We are going to put in numbers, and because you have to answer which of the twins is younger. So, I will put these numerical values. So, we are at rest here and someone starts accelerating along the x axis. Initial conditions at rest. So, ui at tau equal to 0 has only a time component, starts at rest, okay, and I take t equals tau to begin with because it is at rest. So, it will have only one component t equals 0, tau equal to 0, and that will be along the time like direction. So, remember I have t, x, y, z, that is my coordinate system. There is a tangent vector along the time like direction. That is the only component that is non-zero. My initial 4 vector velocity lies along E t. Okay? What is the acceleration? It is this magnitude g along E x. So, remember the acceleration's magnitude is the same as my 3 acceleration, yeah, as experienced in the rest frame. So, I am starting from rest. I have these initial conditions and I have these 3 constraints that have to be obeyed at all times. ui is minus c square, ui ai is 0, ai is g square. So, okay. The problem is set up. We have to solve the problem subject to these 3 constraints written in the last line. Okay. All right. So, let us write down these constraints explicitly. ui equals minus c square. My signature is minus plus plus plus. So, the first of these equations, this fellow. So, I am going to write all these open in explicitly. There will be only t and x components, y component, z component is 0. Right. ui is minus c square, that is this equation. There is a ut component, there is a ux component of the 4 velocity, and that satisfies this. ui ai is 0, that is this statement, yeah, and ai is g square, that is this statement. So, please have a look at it, see that you are satisfied. Those 3 equations written in terms of components become these 3 equations, and we are looking for a solution. Let us try the following solution. ut is c times cos hyperbolic a tau, ux is c times sin hyperbolic a tau. Put this solution, let us put it here, then cos square minus sin square is 1, okay, and there is a c factor in front. So, this equation is automatically satisfied by this proposed solution for any value of a. Let us put this here. Ut time derivative is sin hyperbolic into cos hyperbolic with the a in front, minus sin. Ux time derivative is cos into sin to the, so obviously this will cancel. The first equation is satisfied, second equation is satisfied. Let me do this one here. You can very easily check that this will be satisfied so long as, because if I differentiate, a will come out, there is a c in front, ac is g, so a is g by c. So, I have solved this system, these 3 equations by this solution, hyperbolic solution, where a is g by c. So, what is my 4 velocity? The solution c cos g tau by c, that is coming from here, c cos g tau by c along the time direction, plus c sinh g tau by c along the spatial direction. What is the acceleration? Acceleration is du by d tau. So, do that differentiation. G tau by g by c will come out, c will cancel. So, g sin hyperbolic along Et and g cos hyperbolic along Ex. So, I have solved the problem now. I have solved for velocity and I have solved for the acceleration. Right? So, we remember what was the solution earlier? The non-relativistic problem, V equals u plus At. U initial velocity put as 0. So, V is At or Gt or G tau. Of course, firstly T and tau have become different, that is very important. And what is the solution? The spatial component, instead of A tau, instead of At, I have sinh g tau by c. What happens for small g and small tau? Sinh x is e to the x, just x, no? Sinh x is x. So, that is g tau by c. C cancels, you get g tau. You get the non-relativistic solution for small g and small tau, so long as g tau is small. What is happening to the velocity as tau goes to infinity? We will come back to that. The sinh will blow up, but you have to take care of the time component also. So, we will come back to this in a moment. And the 4 acceleration is given by this, its magnitude is always g square. Its magnitude of the 4 acceleration is always g square. So, now we can answer the twin paradox because we have the solution. Question: after travelling for a time t as measured by the accelerating observer, so proper time. In the accelerating observer's frame, suppose time t has passed, I am accelerating, I have a clock, some time capital T has passed, how far has the observer travelled? I want to know if some time capital T passes in the, where capital T is the proper time, if some time capital T passes in the accelerating observer's frame, in that much time how far did they go? How to do that? Look at ux. What is ux? Ux is dx by d tau. Ux is dx by d tau. So, dx is ux d tau integral from, so this is the distance travelled in a time capital T. Are you okay with this? Substitute for ux from here, c sinh, and sinh integral will be cos hyperbolic, there is a c outside, and then when you integrate, you divide by g by c, so you get c square by g. This is an interesting number, c square by g, you can check has dimensions of length. Length square by time square divided by length by time square. So, this is length. This is an important quantity to remember because the rest of it is dimensionless. So, this integral gives you cos hyperbolic, and the upper limit it is cos, I should have put t here. Here tau is t. So, another typo, g t by c, lower limit is 0. So, there it is 1. So, please correct this typo, this is not tau, this is t, g t by c minus 1. Now, which I want to compute this, I want to do a numerical calculation, put this t as 10 years, g is 10 centimeters per second. You, by the way, just estimate this number is huge, c square by g, g is 10 meters per second square, c is 3 times 10 to the 8, c square is 9 times 10 to the 16, about 10 to the 17, 10 to the 17 by 10. It is 10 to the power 16 meters. It's a huge number, very interesting. At terrestrial acceleration, this is a very big number, and if you put t as 10 years, you can check this comes out to be. So, in my frame, only 10 years have passed. If I am accelerating, 10 years have passed. So, I might think that I should travel 10 light years, even if I am at the speed of light, which I am not. So, at most 10 light years, but this is what I am traveling. Already this is telling you that in the, because this distance delta x is in the lab frame, my frame, I am static here. Already this is telling you that there is going to be a huge time dilation, right. So, some very many years must have passed for me to cover this many light years. So, let us ask now, how much time has elapsed back in the original frame while doing this? 10 years have passed for the accelerating observer. I am here. How much time has passed for me? Ut is equal to dt by d tau. Okay? So, ut d tau is dt, is delta t. Ut is dt by d, c dt by d tau. So, delta t is just ut d tau by c integrated over time interval 0 to t. Time t has passed in the accelerating observer's frame. So, ut is given by this cos hyperbolic, the time component, integrated sinh and put the time limits, and lo and behold, for 10 years you get now you know who is younger. The guy was not accelerating, has 14,639 years passed, and the accelerating guy only 10 years have passed. So, the accelerating fellow, the twin paradox, the guy who went and came back is younger, and you compare this in these many years, in 14,639 years, the accelerating observer has travelled 14,638 light years, almost at the speed of light. You know, it picks up very rapidly, yeah? Does not take that long. You start with 0 speed and 10 meters per second square, so you will be going very fast very soon. Okay. So, tell me how it's going, stop me, everything's okay?
Just to compare, if we start with this calculation and if we can calculate the final acceleration, the velocity of this observer
Yes.
after 10 years, we choose that velocity and do the time dilation calculation using special relativity. So, how would this change?
This is the paradox. How is the paradox being solved?
No, not the solution. Here we are getting a huge number, 48,000 or something.
Which number? First or second?
It's in time.
Second time, delta t.
Just to get a comparison, suppose we choose the final velocity of this observer.
Very close to speed of light.
Then do this 10-year time dilation using special relativity.
For that speed, you will get something like this only, because it's very close to the speed of light. I hope I am understanding your question. For that speed, do the time dilation. Yeah, it would be a big number. It's close to infinity, no? V is almost c, delta time dilation, my time delta t is gamma times the proper time. Proper time is less, gamma is very high, gamma is 1 over root 1 minus v square by c square. So, 10 years into gamma, which is nearly infinite. It will probably be even more than this, it will be more than this, yes? Okay, no? Gamma times 10 years, where gamma is 1 over root 1 minus v square by c square. Yeah. It will be more, because this fellow is picking up speed, That fellow, your fellow is already okay. Okay. So we want to go one step further. We want to also find the trajectory. Instead of x equal or s equals half gt square, what is the trajectory? What should I do? The four velocity is dxi by d tau, where xi is the 4 vector. So I integrate this. Just integrate this, so you will get the trajectory. So this is the answer. There will be a constant. Trajectory of the uniformly accelerating observer, integrate the 4 velocity. This is the trajectory. Ct equals Ct naught, that is a constant, plus c square by g, sinh g tau by c. X, how does my position change with proper time? X equals x naught plus c square by g cos hyperbolic g tau by c minus 1. So, starting time was, suppose I start at tau equals 0, I can put, let us say, suppose we will work with starting time t naught is 0 and tau is also 0. So, at tau equal to 0, cos is 1, 1 and 1 cancel, so x is x naught. So, I start at x equals x naught at t equals tau equals 0. That is one simpler solution. What is the 3 velocity of the accelerating observer? 3 velocity is dx by dt. 3 velocity as seen by me, that is dx by dt, which is the same thing as ux by ut. Ux is dx by d tau, ut is dt by d tau cancels. So, ux by ut, you see here, ux by ut is tan hyperbolic, right. My 3 velocity, the 3 velocity of the accelerating observer is given by this. So, now we can see never approaches the speed of light. For tau going to infinity, tan hyperbolic goes to 1, sin over cos, tan goes to 1. So, in the asymptotic limit, my speed goes to c, speed of light. So, this is the resolution of the Newtonian mechanics problem. For small tau is g tau by c, c cancels, is g tau. Its 3 velocity is g tau, which is how it should be, v equals u plus at. But now that at has been replaced by the tan hyperbolic function, which does not go to infinity, which settles to 1. Okay? So, this is the constraint imposed by special relativity. So, you can ask yourself where it is coming from. The speed of light is the maximum bound. So, ui is c minus c square, ai is 0. All the equations are combining to give consistency with special relativity. Use this to work out the Lorentz transformation that takes us from the inertial coordinates Tx to the coordinates t bar x bar corresponding to their MCRF. What was the MCRF? The frame with respect to which I am momentarily at rest. There are different MCRFs at different time tau, yeah, because your speed is going up. So, you need a different MCRF. That MCRF, let us say, has coordinates t bar x bar. How can you find those coordinates? Make a Lorentz transformation. If the MCRF, if momentarily your speed 3x speed is Vx, you will find your MCRF coordinates by making this Lorentz transformation. So, you can see from the first equation that t can be written like this. T is the time in the inertial observer's frame. T bar is another inertial observer, the MCRF observer. If you put t bar as some constant, you want put t bar as some constant, Vx is given, t becomes a linear function of x. This is a straight line. What am I trying to do? I want to see what does the t bar equals constant look like in the tx plane, because what is t bar? T bar is the time in the MCRF when your speed is Vx. Okay? So, I want to plot these lines, t bar equals constant, you can see is a straight line, the slope will go up as Vx goes up. See the diagram on the next slide for trajectory of the accelerated observer and lines of constant t bar. Lines of constant t bar gives you the time at which the time at in the MCRF when your speed is Vx. Okay? Any questions here? Okay. So, I hope this diagram is clear. What is happening in this diagram? Ct, t on the vertical axis, x on the horizontal axis in units of c square by g. C square, array yaar. C square by g has units of length. So, I am plotting on the x axis lengths in units of c square by g. So, I start at x equals c square by g, that is my starting point. That is what I get at tau equal to 0. Let us go back here for a moment. So, at tau equal to 0, x is equal to x naught. I put that x naught as c square by g for this trajectory. Okay? I start at c square by g, and this is my curve. Okay? So, we will look at it little more carefully. This is the t over x plot. Okay? How do I plot that? T is going as sine hyperbolic, x is going as cos hyperbolic. So, essentially t by x is tan, no, t by x will be tan hyperbolic. So, choose a value of tau, find x and t, plot it, choose a different tau, find x and t, plot it. And these lines, these straight lines are lines of constant t bar. Okay? And so, how did you find t bar? T bar depends on the straight line, the slope is given by Vx by c square, and Vx is tan hyperbolic of tau. So, if you choose a value of tau, you will know the slope of the line. That is what being shown here. For different values of tau, you get different slopes increasing. These are t bar equals constant lines. This is the trajectory of the uniformly accelerating observer. You remember, I do not want to switch. I had drawn t going as 1 over root s. So, this is essentially that curve, but soon we will see what are the restrictions. Something very interesting happens. So, what is the, well, let us read the label. World line of an accelerating observer that starts at x equal to c square by g, as the red curve, and 3 examples of the constant t bar coordinates of that observer's MCRF at different moments along the world line. So, as you are speeding up, the MCRF is changing to higher velocities, and you will meet that MCRF at different times, and those times are given by t bar, and t bar equals to constant are straight lines in this plot, and higher values of t bar, then that MCRF meets you when as your speed goes up. The MCRF time t bar coincides with the observer's proper time where it crosses the world line. Notice both axes are in units of c square by g. Main thing, not so much t bar, main thing I just wanted to show you this plot as compared to s equals half gt square in the Newtonian case. Any questions? There's an online question. Where should I go?
They are asking what is MCRF and can you explain it in?
Okay, what's the question?
So they are asking for MCRF.
What is MCRF?
Concept of
Momentarily co-moving rest frame. What does that mean? I am accelerating along the x-axis, my speed is going up. Suppose my speed here is v1, when I reach here it is v2. Suppose a car is moving at a speed v1, then I will be at rest with respect to that car here. But here my speed has become v2, there will be some other car going at speed v2 with respect to which I will be momentarily at rest. So, the car or the frame with respect to which I am momentarily at rest is the MCRF, and MCRFs keep changing. When my speed is v1, I have one MCRF. When my speed is v2, I have another MCRF, and so on. Yeah. Now, we move on to the next very interesting. We have solved for the trajectory of the uniformly accelerating observer in special relativity. Now, I want to ask this important question: how does the accelerating observer describe space-time? What does that mean? We will set up something known as Rindler coordinates, in which accelerating observer is at rest and proper time acts as the time coordinate. Let us try to understand what is the significance of Rindler coordinates. Any observer can use whatever coordinates they want, but some coordinate systems are special. Suppose I am at rest here, okay, so I am sitting, let us say, at x equal to 0 or x equals x naught. I have draw coordinate system, let us say t x. Yeah, I am at rest at x equals x naught. The constant t lines are in the vertical direction. Sorry, time is increasing. Yeah, that time is my proper time. The coordinate time is also my proper time. Why? Because I am at rest in this frame. So, d tau square is equal to dt square minus dx square. Dx is 0. D tau equals dt. If I draw a tx coordinate system in this lab, I am at rest at some particular value of x, and the coordinate time t is also my proper time. Do you understand this? It's very simple, right? I want to do exactly analogous thing for the uniformly accelerating observer. In my coordinate system, his position is changing all the time. He is speeding up and he is not at the origin. His position changes, obviously. I want a new coordinate system in which his position does not change. Co-moving coordinate, or so he is accelerating, but in that coordinate system his position should be some constant. We will call it x bar. Moreover, that is not all. What time coordinate do I want in this new coordinate system? It should be his proper time. The clock that he is carrying is running at some rate, that is the proper time tau, or here now called t bar. That t bar should label the entire new coordinate system. Okay? I want to label the new coordinate system as ct bar, x bar, y bar, z bar, okay, which has the property that t bar is the proper time of the accelerating observer. So, t bar should label the whole new coordinate system. Instead of xt, x bar, t bar, x bar is where the accelerating observer is at a fixed x bar, and t bar labels his new coordinate system. T bar is his proper time. Please assure me that you get this. It is very important. Rest is straightforward. There is a significance of the Rindler coordinates. They are very special. For the accelerating observer, they are like his inertial coordinates. He is not inertial, he is obviously a non-inertial frame uh, because he has a non-zero acceleration, but he can set up coordinates in which he is at rest, and his proper time labels the whole coordinate system, just as for an inertial observer the time t that labels the Tx diagram is also his proper time. Okay? All right. So, first I will give you the result, then we will in the end prove this. Rindler coordinates x bar, y bar, z bar, t bar are given by these relations. X and t, inertial observer, t is the coordinate time, also inertial observer's proper time, x is the spatial coordinate, y and y bar are same natural, z equals z bar, and t and x are related to t bar and x bar as Ct is x bar sinh gt bar by c, x is x bar cos gt bar by c. We will prove this, we will derive this from first principle. Right now I take it as a result and I want to show the interesting properties that it has. In the barred coordinate system, the accelerated observer is at constant x bar given by c square by g. Why I chose this number? Start at t equals t bar equal to 0. At t equal to t bar equal to 0, x is equal to x bar, t is 0, t bar is 0, t is 0, and x is equal to x bar. Look at this solution. At tau equal to 0, this term vanishes, x is equal to x naught. That constant I make a choice, origin is up to me. I make the choice that at the beginning I am at the coordinate x equals to x bar equal to c square by g. So, I am going to carry this coordinate with me all the time. I mean, if I am the uniformly accelerating observer, my x bar is fixed and it is fixed at c square by g. Yeah? But of course, in my coordinates, in my accelerating observer's coordinate system, x bar will have different values at different locations. Similarly, t bar will have different values. So, my t bar will change because time changes, but my x bar is fixed. The barred coordinate t bar is the same as the proper time tau of the accelerating observer. See diagram on the next slide for understanding how Rindler coordinates look in the inertial frame. We will go there in a moment. What does this line mean? Given x and t, I can plot x bar and t bar as functions of x and t. I can just invert this. Yeah. What is the Rindler metric? In t and x inertial frame coordinates, this is the Minkowski metric. All I do is I make a substitution, dt is dx bar sinh plus x bar sinh dt bar, do the differentiation, substitute for dt and dx and simplify. This is the answer you will get. This is the Rindler metric. Yeah? It is, you can already see that it is non-trivial. The components are no longer constant. The time component depends on x bar. Okay. Yeah. So, this is the first example we see of a non-trivial metric where the components are not Minkowski. I am still in flat space time. So, these are curvilinear coordinates in flat space time. There is no gravity but hence the Riemann curvature tensor will be 0. Yeah, if you calculate Riemann for this, it will be 0. The Christoffel symbols will be non-zero. Yeah, because it's non-trivial. Why are the Christoffel symbols non-zero? They represent the gravitational force. The force is there, gravitational force is there, but because it is uniform, there is no Riemann tensor, there is no curvature. Why is there a uniform gravitational field? Equivalence principle. I am accelerating, but that cannot be distinguished from an inertial frame with the gravitational field. You get that, no? Either I am accelerating here with the acceleration g, or there is an inertial frame in which there is a uniform gravitational field g, and hence this will be the metric. It is a non-inertial, it is a curvilinear coordinate system. The gammas will be, if you write down the geodesic equation, you are still moving along a straight line, but you will get as if you are moving in an inertial frame with a gravitational field. Okay? So, this is the Rindler metric. These are the Rindler coordinates, and we want to now see some interesting properties of these coordinates. So, first, let us spend some time with this diagram. Ct, x, these are inertial coordinates. Let us read this, an illustration of Rindler coordinates. The red curve is the world line of an accelerating observer who starts at x equals c square by g and experiences constant acceleration g. Here, c square by g units, so c square by g equals 1 means x equals c square by g. This is the trajectory starting at x equals 1 of a uniformly accelerating observer, which is what replaces what you have in the non-relativistic case. The green lines are surfaces of constant t bar, the same that we talked about, which coincide at that observer's location with their own proper time. Yeah, these are lines of constant t bar, the time in the MCRF, same as the proper time. So, different t bar values intersect this line at obviously at different proper times. The blue curves are trajectories of constant x bar chosen to coincide with the unaccelerated frames x when t equal to t bar equal to 0. So, different constant values of x bar will give you different accelerating observers. These are all like the trajectories of accelerating observers, these curved lines. Why? They start at different x bar. Okay? So, what is x bar? X bar equal to c square by g. If your x bar value changes, your g value changes. You start with a different uniform acceleration. Depending on the value of your uniform acceleration, you are starting from different points. Higher the acceleration, lower the value of x bar, you will move closer to the left. So, blue curves are trajectories of constant x bar chosen to coincide with the unaccelerated frames x. I hope you understand this, when t equal to t bar equal to 0. So, at t equals t bar equal to 0, x is equal to x bar, but you can have different values of x bar, meaning different values of g, and you will get different curves of different trajectories, different accelerated observers, different g. A heavy black line Ct equals x, this one diagonal, illustrates a light ray that is emitted from the origin and moves to the right. Notice both axes are in units of. So, now we get to this very interesting. So, you have seen trajectories of accelerated observers. Now, see what is happening. they are all asymptotically, this trajectory at x equals 1 is asymptotically tangential to the direction of the light ray. Yeah? So, that has important consequences, just keep this in mind. There is a horizon. A light ray starting at the origin and travelling along plus x direction never crosses an accelerated observer's trajectory. That is clear, there is no intersection. The light ray asymptotically approaches the accelerated observer's trajectory as the proper time t bar goes to infinity. Yeah, that is what is happening here. There is a region of space-time which can never communicate with the accelerated observer. No signal sent by an observer to the left of that light ray can reach the accelerated observer. So, if you extend this x axis to the left, suppose from here you send a light ray like this, it will never reach, I will explain this more visually, it will never reach the accelerated observer. We say that there is a horizon separating the events which can communicate with the accelerated observer from those events which cannot so communicate. So, let us spend a few minutes understanding this horizon. It is very remarkable. I want to visualize this. It is not so easy to visualize in a space-time diagram. We cannot imagine space-time diagrams, but we can imagine space. Okay. So, now just for visualization, I make my x axis like in this direction, not in this direction. This is x axis. I am the one who will accelerate and go in that direction. Yeah? You are all my friends. I imagine that you are all sitting in a straight line. You are all sitting along the x axis. You all have a torch in your hand. When the time t equal to 0, when I start, please switch on your torches at the same time. What this result is saying that, so you are at different distances, okay? There is a critical distance c square by g. I am here, your distance from me is changing as you go deeper. That distance is c square, there is a critical distance c square by g. For g equals 10 meters per second square, c squared by g is around 10 to the power 16 meters, some huge number, 10 to the. So, now one of you is sitting at 10 to the power 16 meters. All of you start your torches when I start accelerating. What this result says is your light beam will catch up with me. I will see you. When your light beam catching up with me means I am seeing you. Yeah, that's when I will see you when your light signal arrives. But if you are beyond c square by g, if you are beyond 10 to the 16 meters, your light beam will never catch up with me. I won't see you. That's the horizon. I can't see beyond. Right? You understand now. Now add x, y, z. Y, z directions are irrelevant. Make a plane perpendicular to the x axis at a distance c square by g. The whole region beyond is invisible, as if it is like an inside of a black hole. It's so very difficult, not so easy to visualize here, but much easier to visualize when I am accelerating in this direction. If you are too far, your beam of light sent by you will never reach me. It looks a bit counterintuitive, because I am always traveling at the speed less than that of light. Your beam is always coming at the speed of light. So, one might think that it will eventually catch me up, but it does not happen, because I am speeding up. If I was moving at a uniform speed, it will catch me up, but I am ever speeding up, approaching the speed of light. You started too far. If you start too far, you do not catch up. That is what the meaning of that this distance is c square by g. if you start too much to the left, like this is, you send a torch beam, you send a signal from here, from where the arrow is, you send a signal 45 degrees, it never reaches the, so that is the meaning of the horizon. It's really deep. You're in flat space time, there's no gravity, but you have a region which you cannot access. It has dramatic consequences in, if you now try to put a quantum particle or quantum fields in this situation, which is what Ashmita will talk about today afternoon. So, in that sense, there is this very interesting analogy with a black hole. I am just accelerating and it seems there's stuff, there's a part of the space time that I cannot see. So, if you want to say something. No, I am at g. I am at g. Some number 10 meters. I am at a uniform acceleration g. Change the value of g if you want. So, if g is small, x bar equal to c square by g will be larger and larger. So, the horizon distance will be larger and larger if you start, sort of understandable. You start with very high accelerations, the horizon will come closer, because you are traveling already so fast that even nearby fellows cannot catch up with you. Yeah? Right. So, so now this is the last part of the talk. I said the Rindler coordinates are x bar and t bar, and they are related to the inertial observers x and t by this relation. I didn't prove this, I want to prove this, where x bar equals constant at some value c square by g for the accelerating observer. X bar will label the whole coordinate system, but it is constant for the accelerating observer, and t bar is the accelerating observer's proper time. Okay, so derivation of the Rindler coordinate system. The accelerated observer uses the time coordinate along their world line to be t bar equals tau. Can this same t bar be used away from the world line as well? You understand what I am saying? In my rest frame, clocks are running at t bar equals tau. That's okay. But elsewhere, I am not everywhere. No, elsewhere, I want to label space time using tau or t bar instead of t. Instead of x and t, I want to label it by x. Instead of x and t, x bar and t bar. So, what do we need? Start by defining unit vectors pointing along t bar and x bar. Natural, no? You want to make a new coordinate system, you want to know what are the unit vectors. Unit vector along t bar. In the accelerating observer's MCRF, momentarily co-moving rest frame, the 4 velocity has components c 0, 0, 0. Yeah? In the MCRF, I am momentarily at rest, so the spatial components of the velocity are 0. The time component is dt equals dt bar and dt will be the same. The time component is just c. So, the 4 velocity in the MCRF has only a time-like component. Hence, define E t bar to be parallel to this observer's 4 velocity. I hope you see this. In the MCRF, the 4 velocity of the accelerating observer is time-like. So, the time-like direction should be parallel to the 4 velocity of the uniformly accelerating observer. So, the unit vector along the direction E t bar, be very careful, t or t bar, I want unit vector along t bar, and that unit vector is parallel to the 4 velocity, because the 4 velocity is time-like in the MCRF. The solution for u I know, we solved for the 4 velocity that had a component along E t and along E x. Let us remember that. This is the solution for the 4 velocity. It has a component along time, it has a component along space. So, I define my E t bar vector, the unit vector along the Rindler time t bar, as just equal to the unit vector along the 4 velocity. Okay? Define E x bar, the unit vector along the x bar direction, to be orthogonal to be the unit vector along t bar. E x bar is just make sure that the product E t bar dot E t bar dot E x bar should vanish. Cos sinh E t square is minus 1, cos sinh E x square is plus 1. So, these cancel. So, this E x bar as defined here is now perpendicular to E t bar. So, I have defined unit vectors in the Rindler coordinate system. So, not x and t, x bar and t bar, and these are the unit vectors. Define a surface of constant t bar. So, imagine what are we doing? I have in the inertial coordinate system, I have t x, I have t and x. The constant x lines are parallel to the time direction. The constant t lines are parallel to the x axis. So, I want to know if a surface of surface quote unquote of constant t bar will be parallel to E x, obviously, no. A constant t bar parallel to the x axis, which is now x bar. E x has a slope of E x in the t x plane, that will be the slope in the t x diagram is E t by E x, which is tan hyperbolic g t bar by c, just this. So, my surfaces of constant t bar are lines with this slope in the t x diagram. Also, this line must intersect the trajectory of the accelerating observer. So, maybe getting a little involved right now, but otherwise very basic. In the t x diagram, draw a line with this slope, which intersects the trajectory of the uniformly accelerating observer. The trajectory solution we know. So, y equals m x plus c, m is the slope, and c is determined by saying that this line should pass through the trajectory of the accelerating observer, and you will find that this is the solution. So, this is surfaces of constant t bar. A surface of constant t bar satisfies this relation C t equals x times that constant. So, these are straight lines. Surfaces of constant t bar are straight lines. So, we know how to draw surfaces of constant t bar in the C t x plane. How to draw surfaces of constant x bar? This should be parallel to the time like vector E t bar. So, what do I want? Surfaces which are constant x. So, they should be parallel to the time direction, which in this case is t bar. So, we can just do a little bit of maths, just like, and show that the slope of the line parallel to E t bar is given by this relation. It's very easy to work it out. Just please check it out. And now integrate this, and this is the solution. Surfaces of constant x bar. surfaces of constant t bar satisfy this relation C t equals x tangent. Surfaces of constant x bar satisfy this relation. So, want to know given x and t, how to find surfaces of constant t bar, how to find surfaces of constant x bar. Here the lower limit in this integral is x bar, because to begin with x is set equal to x bar. I want to solve, please stop me if this is not clear, just stop me. Yeah?
So that formula dx by dt is equal to c tan h. So I think it should be dt by dx.
Yeah. So, dt by dx is cot. I reverse that. You are right. The slope dt by dx, where is this?
The last line. So if you take the derivative on both sides, it should.
No, not from here. This is surface of constant t bar. I shouldn't use this right now. I want surfaces of constant x bar. Look at for that I have to look at Ex, no? I have to look at Ex. Surfaces, no, sorry, I have to look at Et. Surfaces of constant x bar will be parallel to Et. So, look at the slope of Et, it is cos over sinh, that is cot hyperbolic, and that is dt by dx. So, dx by dt is tangent, right. And now to write this tangent, I use this relation. Tangent is Ct by x. Okay. So, I put that as, so that is how this comes. You do this integration. This is a hyperbola. Surfaces of constant x bar are hyperbolae, and that is what we saw in the solution. Surfaces in that diagram, surfaces of constant x bar were hyperbolae, and this is satisfied by this hyperbolic solution. And if the value of alpha is fixed by using this relation, and finally, you will find that x is x bar cos g t by c and t is x bar sinh g t bar by c, and finally, this is what you have. Yeah, this is these are Rindler coordinates. Therefore, we now have a complete mapping of the accelerated observer's reference frame into the initial observer's reference frame. These are, so we have, sorry, it was a little fast, but you have the slides, you can see the slides on the link, and you can, this is the derivation of the Rindler coordinates. This is what we used here to deduce the horizon. Okay. So, the trajectories are surfaces of constant x bar. So, along a trajectory x bar is constant. So, these are different constant values of x bar, constant at c square by g. Yeah. Okay. And t bar and t are related like this. T bar changes, the proper time changes, t bar changes with t, and x bar is a constant, different constants for different observers, and this is how the inertial coordinates t and x relate to the Rindler coordinates t bar and x bar. And this maybe I will leave some time for discussion. What is being done in this last point is that if an observer at constant x bar is an accelerated observer, what acceleration does such an observer feel? So, you start with some value of x bar, you always have that x bar. Yeah? What is your acceleration? You can do, please do this calculation, that your acceleration, the acceleration that you will experience if you start with the coordinate x bar is c square by x bar. The x bar was c square by g, now g, the acceleration is c square by x bar. So, in this diagram all these hyperbolae are different accelerating observers with different values of x bar as expressed in units of c square by g. So, this is a very simple calculation. All you need to do is compute the 3 acceleration, because we know that the 3 acceleration as measured in the MCRF. So, at t equals t bar equal to 0, all x bar constant observers are momentarily at rest. Everybody is starting at rest at t equal t bar equal to 0, but with different values of x bar. So, your 4 velocity is this, your 4 acceleration is this, because you are all in the MCRF, and then you want to find A x, which is d 2 x by dt square, and you can find this by transforming to dt bar. Instead of differentiating with dt, differentiate with dt bar, and you know how t and x depend on t bar. So, you do that calculation, very straightforward. So, if you are carrying a coordinate x bar, your acceleration is c square by x bar. Yeah, okay.